it is an equation that looks like y equal f of x, y, and let me say it another way. That's a separable differential equation where y prime is the first derivative. Imagine that. Good land. I don't think I've ever seen your ears before.
Me?
You.
I got a haircut.
Yeah, they were lower. Where y prime can be written as some function of x and y. So first thing is, it must be able to be written with y prime on one side, the x's and y's on the other. And by the way, that's not always the case, but it's a special form. Then the second equal sign says that it must be able to be written with all of the x's together in a parentheses times all of the y's together in a parentheses. That's what the two are. Now, my way of saying it naturally is somewhat different, and that is a separable differential equation is one in which we can get all x's, including dx, on one side of the equal sign, and all y's, including dy, on the other side. To solve it, we integrate both sides. That's how separable DE works. In differential equations, the first day of class, you know me, I have class on the first day of class, right? And DE is a hour and 45-minute class on Tuesdays and Thursdays, and I will spend the first day doing separable differential equations. They'll be a little bit harder than what we're going to do in Cal 2, but this is what I do first in DE because students have seen it. And you remember I spent a little bit of time last time telling you that the differential equation has y prime in it, and our goal remains, as is often the case in algebra, to get y equal. But the complication there is now I've got a derivative in it. And all I'm saying is if I can get all of my x's on one side and all of my y's on the other side, then I just integrate both sides and I no longer have a derivative. Does that make sense? Because you know that integrals undo derivatives and derivatives undo integrals. So with all of that, it's time for an example, because this is one time in calculus. It really is as easy as it sounds. This is example 1 on page 429. We'll leave that y is greater than -1 alone for right now, and we'll talk about it in a minute. Does that look like a differential equation to you? And doesn't it look like the derivative on one side and the and x's and y's on the other side? Huh? Now, just as y is equal to f of x anytime I want it to be, anytime, no explanation required, anytime I want it to be, no explanation required. They're the same thing. You agree? You learned that in Cal 1, didn't you? Okay? So, I think that this is, agreed? Now, what I'm going to do you remember what I said? What I'm going to do is I want to get all my y's on one side, all of my x's on one side. Doesn't matter which side, whichever one suits you is fine with me. Okay? This one, it looks to me like all I have to do is divide by this and multiply by this. If you look at that a minute, doesn't that accomplish exactly what we want? I'm going to stop and give you a minute to look at it. And my goal is to get x's on one side, y's on the other. Is everybody okay with the plan? So I think what I have now is, I think I have 1 over 1 plus y dy is equal to e to the x dx. And is that slick or what? Because now you can integrate both sides, can't you? I'll get the right side, you get the left side. What about that left side? What is it? What? You guys are a little bit slow on the trigger. What's the derivative of 1 plus y?
Then 1 plus y is 1.
So don't I have the function in the numerator and the derivative of it in the denominator? When that happens, what are you supposed to think? What are you supposed to think? Beth, do you think they're asleep or what? What's that equal to?
Natural.
Natural log of x? What's that equal to? What?
Natural log of x. What's natural log of
Plus 10. Natural log of x plus 10, huh? Anytime you have the integral of some function g of x and its derivative in the top, anytime that's equal to the natural log of g of x. Anytime. Y'all got to get faster on that. That's one that just comes up over and over and over and over again. And you will as you work homework problems on this. Okay? So I think this is the natural log of 1 plus y is equal to e to the x plus c. Everybody agree?
C on the left.
Yes, that's a good question, Spencer. Spencer says, shouldn't you have a C on the left also? And the answer is, yeah, you sure should. But if I've got an arbitrary constant on the left and an arbitrary constant on the right, when I move this arbitrary constant on your right, I forget about, y'all are seeing this in the opposite direction. If I move the arbitrary constant from your right over to your left, what is an arbitrary constant minus an arbitrary constant? What? An arbitrary constant. Do you follow? What I'm telling you is, didn't I just snatch C out of the air anyhow? So if I add or subtract two numbers that I snatched out of the air to begin with, guess what I get? One that I could snatch out of the air. And that's why I write it that way. Absolutely, and there will be times in differential equations that we have to keep up with C1 and C2. If we'd have done it we'd have called the one on the left C1, the one on the right C2, right? And there are times you have to keep up with it, but almost always it doesn't matter. But if you want to do it, by all means, it's okay. Now there's another little issue. There's another little issue left. For me, that answer's fine. That answer's fine. But let me remind you that if you wanted to graph the solution in any of these TI calculators, when you go to graph, what is already on the screen? Y equal, right? Which means you're out of luck unless you can get to Y equal. So let me give you a hint. Hear me again. To me, this looks fine. This looks fine. That expresses a solution. And I can get Y equal if I want it. When I do it, I don't think it's going to look any better than that. In fact, I'm expecting something pretty ugly. Okay? I could get to y equal if I could make that log go away. Do you agree? If that log wasn't there, wouldn't I just have 1 plus y? Everybody? So I need real badly for that log to go away. Daniel, you know how to make it go away? I'm not going to ask you if you don't know, because I don't want to put you on the spot. That was an expression of confidence, you notice, huh? Anybody?
E to the X.
Not only did he get a haircut, he's the gold star student today. The way you make a log go away is with an exponential e, and the way you make an e go away is with a log, huh? So I'm going to what do you think exponentiate means?
Initiate exponential.
Exactly what you told me to do, right? And that is, I'm going to take both sides and make them be the exponent for e. I can do that, can I, if they're both equal, right? Everybody agree? Everybody agree? So what I'm telling you I'm going to do is, did I do what I said I was going to do? Daniel, what's wrong? It is about to help us. It is about to help us. What are you supposed to notice? It's supposed to just jump out at you, right? Aren't you supposed to be able to take these two and do that? Everybody agree? And now I have 1 plus y is equal to e to the e to the x times e to the c.
Let's send me exponents on the right.
Do I?
When does the exponent stop on the right? I mean, why not a few more? There's 2 of them.
I took the whole right side, whatever was on the right side, and made it the exponent. And when you're adding exponents, doesn't that mean you multiply outside the exponent? Frankly, guys, I don't know that that helped it any. I just did it so I could remind you of handling exponents. How do you say that that's any prettier?
If you did your final answer, e to the c, it wouldn't be e to the x plus c? Like it wouldn't be in the it wouldn't be in the initial exponential on the first
No.
term?
No, and the reason is, if this plus c were up there with the x, then it would have been.
Okay. But it wasn't.
Everybody okay with that?
You can graph it now, though.
You sure can, and that's my point.
That's awesome.
So now I have y equal e to the e to the x times c minus 1. Anybody want to explain to the class why the old man thought he could get away with calling E to the C just C?
It's the exponential of
Travis, what?
Just another arbitrary constant.
Yeah, if I take the exponential function and raise it to some arbitrary number, any number I pick, doesn't that mean that I'll get some arbitrary number? And that's why. And that's why. Questions? Beth, those high school algebra teachers would just cringe at how sloppy I am with C's. You know that? They would not like it. But you do understand the concept of arbitrary numbers, huh? Okay? And now you can graph the solution. Questions? I wonder if that would check. You can check your answer, can't you? How do you check your answer? Take the derivative of it, and you should get the same thing on both sides. Let's see if my arbitrary constants got in the way of what really ought to be, huh? Okay, so y prime is equal to, let's see, y prime is equal to C E to the x times e to the x. That's what I think it's equal to. What do you think?
Oh, yeah, because it's just gonna be.
So I think this is equal to C e to the x plus 1. Is that right? Which is C, I say, Do what?
It's not e to the x plus x.
That's e to the x times e, huh? Not so nice, huh? Not so nice. What's wrong? I'm not at all telling you that doesn't work. I am telling you, if I were going to check it, I would check it right here. Because what we did is it's not that we changed the problem, it's not that that's not a solution, but the differential equations have more than one solution. I forgot to tell you that, didn't I? But doesn't that make sense? If integrals have more than one value, that's why we put the C on. Wouldn't you expect when you get rid of the derivative in a differential equation, you'd have a plus C out there? And this is a solution that in our gyrations of calling e to the c c, we just changed the form of, huh? And the place to check it is before you start doing all of that. Which gets back, do you remember my original argument? What did I tell you? For me, that suits me just fine. And the only purpose I can think of for you to find y equal is so you could graph it. Okay? Everybody okay with how the method works? And notice, if you notice, when you see your book on page 229, they left it where that red arrow was, at the same place I said I'd leave it. This is example 2 on page 430. First thing you have to decide is that separable? And I can tell you right off that it is. You know how I know? You only know one way to solve differential equations, and if it's not separable, you're out of luck anyhow. That's how I know. But perhaps we want a better reason than that. So what you do is you try to put all the x's on one side and all the y's on the other side, huh? And let's see. Well, I think we can do that. What do you think? I think I'm going to. I think for that, I'm going to divide. For that, I'm going to divide, and for that, I'm going to multiply. Won't that get it?
Sure.
Does that get it? Everybody? So, I'm going to write it, and then you can check me and see. That's the way I think it looks. What do you think?
Is it x plus 1 or is it x squared plus 1?
I don't know. Evidently, I didn't know when I wrote it down either. I think looks like x plus 1 to me. I know why you were wanting to know.
Yeah, they didn't look equal. They didn't look equal just side by side because you have the y squared plus 1 on the bottom. It's x plus 1 on the other side.
I was thinking the reason that Spencer wanted the square there was, then what's the derivative if there's a square there? Wouldn't it be 2x? And that would take care of this x up there. That's why I was wishing it was a square. Alas, it's not. Can you integrate the left side? Yes or no? I want you to start doing this. I want you to make this your new thought process as things gets harder. And that is, simply ask yourself, can I integrate that? And look at it and develop a plan before you write anything. I can make the numerator of your right side look like the derivative of the denominator of your right side. Can I not? Yes or no? What's the derivative of the denominator of your right? No, it's your left side. I'm sorry. Look, I want to tell you, this is hard. Let's do the left side first. Your left, let's do the left side first. Your left side, I can make the numerator of your left side look like the denominator of your left side. I mean the derivative of the denominator.
Yeah. Multiply both sides by 2.
Yes. Do you agree? Does everybody agree? Okay. So we know what to do there. We're not going to start doing anything, but we've got a plan. Now your right side. I wish Spencer had been right, don't you? Because then I would have just said, we'll do the same thing, huh? But alas, no. So what do you do? What do you do? And see what I mean by deciding what you're going to do before you start writing? You've worked problems like that. Come on, think back. If I let u be equal to x plus 1, isn't that one of my 5 rules? What would x be equal to?
X minus 1.
Exactly.
Minus 1.
And then nice things happen. So do you see now we've got a strategy and we figured out what we can do, and now we set out to do it? Everybody okay with that? Okay? So what I'm going to say is, you take a look at this and see if it's okay for me to do this. First thing, forget about the half for a minute. Do you follow why I wanted the 2 there? Does everybody know why I wanted the 2 there? Spencer, do you know why?
The 2y at the top?
Because this y squared right here,
Or
when I take the derivative of it, I get the 2y. I knew what you were saying. Agreed? So I said, I need a 2 right there. So I just put 1 there. I just reached up and grabbed that baby and put it there. But if I had left it at that, wouldn't this no longer be equal? Because I changed one side and not the other side? And I don't know if you heard him say it, but one of you, who said a minute ago, multiply both sides by 2? Was it you? Daniel. Exactly. Daniel said multiply both sides by 2, which would have accomplished the same thing. But what I'm trying to get you to do is believe that if I multiply by 2 inside the integral to make it something nice, I can get away with doing that by multiplying by 1/2 outside the interval. Why? Because 2 times 1/2 is what? And I'm not changing anything. And Daniel, I can tell you many, whole bunch of many times I've multiplied both sides by 2. But I'm trying to,
You would have just been left with a constant on the other side.
That's
that you
right.
could pull out anyway.
that's right, it's either way, but I'm trying to get y'all where, see, technically what I should have done is I should have said u is equal to y squared plus 1. Du is equal to 2y dy, and y is equal to, and dy is equal to 1/2 du, right? I should have done that. And I'm trying to get y'all to where on some of them, you don't have to write that out. And that's why I went with 1/2 instead of 2. Everybody follow? Let me say it again. I looked at this problem and I said, I wish I had a 2 right there. And I said, well, since I'm holding the pencil, I'm going to just put a 2 right there. And that's exactly what I did. But then, if I'd have just put the 2 there, I would have destroyed the equal sign. So in order to protect the equal sign, I had to put a 1/2 out there in front of it. Everybody okay with my reasoning? Okay? But, let's see. This then is think that's right? Everybody? Isn't that's slick, isn't it? Gets us out of a jam. So now I've got u minus log u plus c. Point was made earlier, I could have had C's on both sides, right? William, what's wrong?
Oh, you just had to take a bit over there, okay.
Do what now?
You just, I was looking at the other side. I see.
Okay. All I'm doing is I'm working this side and this side at the same time. Okay? And this is equal to,
Why did it split into one du minus 1 over u? Where's your other u?
U over U.
Yeah, your u's
I did,
okay.
this one is the 1, and this one is the 1 over u. And I think that then is x plus 1 minus the natural log of x plus 1 plus c. And I guess I would at least write it as I'll ask the question. What happened to the +1?
Can't afford your.
It got rolled into the arbitrary constant, didn't it? If I'm adding an arbitrary constant, what's the difference between an arbitrary constant and an arbitrary constant +1? Nothing. And right there is where it needs to stay. Could you solve for y? You sure could.
You had to.
Yeah. You had to, if someone were holding a gun to your head. If you had to. What I would do is I would move this over to the other side with a plus sign in it. Doesn't that mean that you put them together inside the log? Remember that gumbo rule I told you? And then I'd take the exponential of both sides, and then I'd try my best to separate it again, and it would get really ugly. And if you think that's bad, imagine what happens to the right side when you start exponentiating and then break that left side up at the same time. Which is what I'm telling you about. Whenever you deal with differential equations, you gotta hear Kenny Rogers in the background. You quit wanting to leave answers in pretty form, because the higher you go in math, the more ugly the answers are going to be anyhow. So you don't bother to pretty them up. Further, sometimes if you move something to a pretty form, something that looks nice, and you want to use it in a problem, the first thing you'd have to do is put it back where it was in the first place. So know when to quit. Have you got the method of separable variables? They all work the same way. The trick is, look at them and decide a strategy for putting the x's on one side, the y's on the other side, and then the rest of it is Cal 2 integrating. But you're going to see lots and lots of logs. Remember what I told you on Friday. Learn to love them. But a log now, I hope you'd say a log now is not bad. All you do is you want a function on the bottom, and you want to get the derivative of whatever's on the bottom and the top. Isn't that all there is to it? Everybody okay?
So the x plus 1, second to last equal sign, because the only thing that I would be able to combine with is arbitrary constant, you could throw that out.
Yeah. Everybody okay? All right. Have you ever heard the saying, if it walks like a duck and quacks like a duck, it's a duck? Not so about hyperbolic functions. Hyperbolic functions are that's one of the strangest animals in all of mathematics. You saw hyperbolic functions in Cal 1, didn't you? And everybody remembers them, right? A hyperbolic function is I have to look the first time I write it every year and make sure I did it right. Oh, and I did. So first thing, why did they use sine, cosine H, cosine H, and tangent H for something that's not an angle?
Probably supposed to be easier. For me it does, I don't know.
Yeah, the answer answer is for convenience. This is part of the beauty of mathematics. First thing, that x in the hyperbolic sine of x is not an angle. It's not an angle. That's what makes them strange, isn't it? We use sine, cosine, and tangent, and you've learned that whatever's inside there is an angle. As a matter of fact, tell me what the x is. Not Ed and Beth, anybody else. Tell me what the x is. What kind of animal is it, is what I want you to tell me. Did I hear somebody say it? Look at the right hand. What?
Exponent?
Yes, sir. Give that man a cigar. Look at the right-hand side. If I'd have just written the right-hand side up there and said, what is x? Wouldn't you have just like that said it's an exponent? So that's what makes this whole discussion so strange, is you're used to seeing, and by the way, as was I, you're used to seeing sine, cosine, and tangent used with angles ever since you were in elementary school. And now they put that h on there, and they start using exponents in the place of it. Do you remember when the first time your trig teacher showed you that sine x is equal to y over r? Did they tell you why it was named, why y over r was named sine x? Or x over r was named cosine x? Did they tell you?
Well, because R is 1.
Do what?
Well, R is 1, and that's about it.
But my question is, why is it called sine x? Why wasn't it called?
I feel like this is a trick question.
Yeah, well, the answer, I'll give you the answer. The answer is there's no reason. There is no reason. It could have been cat x or dog x. Those were just names that we gave them in order to give them a handle so we can call them something. So help me, that's it. That sine x is nothing but a name for a ratio of two sides of a triangle. That's all it is. And cosine x is a ratio of two different sides of a triangle. And tangent x is the other ratio, for the three sides of a triangle. And you had to call them something. You had to call them something. Ed?
Okay. Definition of trigonometry is relationship between angles in a circle, right?
Yes.
This is relation between angles in a hyperbola.
Yes. It really is.
They've got elliptic functions too.
It really is, yes. It really is.
Do they have parabolic functions?
Do what?
They have parabolic.
Yeah, it's a whole different study of geometry. Beth, did you have that geometry course did you take a lot of teachers looking for 18 hours take a graduate course in geometry that is it is a very good course. My son took it, is how I know about it, and it's a very good course, but it talks about different types of geometry. And that's what you're talking about, Ed, is we do Euclidean geometry, but they're all different types, and they're based upon that kind of thing. But for now, all I'm telling you is they were just a name. And I told a class years ago, you know what the H means? You know what the H means?
Exponent, already done exponent.
The H means first cousin. First cousin. It's not an identical twin. It's not even a sibling, but it is related. And that's what it means. The reason we call them sine H, cosine H, and tangent H, and if anybody says sinh and cosh, I'm going to lose it. It is hyperbolic sine and hyperbolic cosine. Your textbook says that. That's what we call them. And I thought about writing them and saying, whoever we is does not include me. But the reason they're called that is amazingly, beautifully, they work like trig functions. And all these are is a name for two exponential functions put together. That's all it is. Isn't that what the right-hand side is? Everybody agree? Now watch what happens. Let me go ahead and define them all. And that is the hyperbolic cosine and the hyperbolic tangent. Now do you see what I mean about cousins? The trig functions have angles as their argument. The hyperbolics have exponents as their argument. That makes them completely different. But yet in some ways they behave the same. In a lot of ways they behave the same. For example, suppose I want the derivative of sine hyperbolic x. With that cousin business, can you guess what that's going to be?
Hyperbolic cosine.
It is indeed. Isn't that amazing, Daniel? The first time I saw that, I thought, wow. It acts like a trig function, and it's not even using angles. Such is the elegant beauty of mathematics, how things fit together. And the more you learn about it, the more it will amaze you. Wait till you get to Cal 4 and you'll see that all that three-dimensional, the first test in Cal 4 is nothing but Cal 1 with 3 dimensions to it. It's the elegant beauty of mathematics, how things fit together. But watch what happens. I think this is equal to this. Hard to argue with that, isn't it? When I just got through saying earlier that those two are equal, it's real hard to argue that that line isn't true, wouldn't you agree? But then I think that is, how do you take derivatives? How do you take derivatives?
One term at a time.
One term at a time. Isn't that what I did? And doesn't that make it an all? Could I have used the quotient rule? Well, yeah, I could have, but doesn't that make it a whole lot more simple? The derivative of e to the x is what? So don't I get e to the x over 2? And the derivative of e to the minus x, I think this is e to the minus x over 2 times a negative 1. And where did the negative 1 come from?
The exponent.
The derivative of the
The
exponent, right? Isn't that the chain rule? Everybody agree? Wow. Wow. And they're not even siblings, much less identical twins. Wow. So, my whole purpose in this, I've taken way too long on this, but my whole purpose in this is to try to convince you there's no hocus pocus, there's no smoke and mirrors. It is simply a name that we gave these exponential functions based upon how they behave. How they behave. I didn't know one of my grandmothers, my father's mother. I knew my father's father, and I knew him well, and he was a wonderful man. And he had the same first name I do, and I even look like him. And the older I get, the more I look like him. And I had 1, 2, 3, 4 first cousins, and of the 4 first cousins, me and one other look like him. Which means that we sort of look like each other. And that's the way I describe hyperbolics. They sort of look like trig functions. Ed?
Did you bring up, how do you access these things on your graphing calculator?
Go ahead, tell them.
It's not easy. You gotta go to the catalog button. And you gotta scan down alphabetically till you get to them.
They're on the newer TI. You know what I did Saturday night? No, Friday night, I took my wife out to eat. I was looking to see if the newer ones had a hyperbolic on there. You do have to go to the catalogs. Anyhow, I went, Friday night at Longhorns, we went in there, and that young man that I told you I had for trig, he sat right there. He and his girlfriend came in, and he came over and talked to me, and I said hello to him, and I was telling my wife the story, and I said, you know, I think I'm going to have a little bit more fun with him. And I said, I went over there and I introduced myself to the young lady, and I said, I'm just checking. Do you really have a pink calculator, and did you loan it to him? And she said, well, yes, I do. I said, well, that's reassuring to know. Oh, by the way, do you need, if you wanted to know the hyperbolic sine of 3, do you need to go to that catalog?
Put in 3 where the E, the X's are.
Exactly. Put in 3 where the e to the x's are and divide it by 2, and don't you find out? You'll get tired of that after a while. You'll want to use the catalog, but do you follow you don't have to? Let's do one more. I can't resist this one. What did that better be equal to? Oh, sorry. What did that better be equal to?
Hyperbolic sine over hyperbolic cosine.
Yeah. How about, didn't the derivative of the tangent, the what? Secant squared? So doesn't that need to be equal to the hyperbolic secant squared? Oh, by the way, what do you think the secant is in terms of the e's? Look at my hands. Wouldn't you expect that it'd have to be this with the cosine? And by the way, it is. But for this first cousin business to hold up, that needs to be the hyperbolic secant squared, doesn't it? Everybody agree? Well, let's see if it is. I think this is equal to the derivative of the hyperbolic sine divided by the hyperbolic cosine. Who wants to tell me what to do next? I'm looking for a 2-word answer. What? Hey, that's good. Travis says substitute the e's and have at it. That'll work. That'll work. Let's see, math teachers used to be math students, therefore math teachers are too much work. Too much work. Looking for a 2-word answer?
Stop there.
Pray hard. How about quotient rule? Isn't that a quotient? And don't I want to take the derivative of it?
Yeah.
They're gonna have to know an additional identity.
Well, let's see how far we can go with it.
Okay.
Bottom squared, right? Everybody agree? How about then the bottom times the derivative of the top? And the derivative of the sine is the minus the top times the derivative of the bottom. The top times the derivative of the bottom. And that is softener. Is that right?
It would be the
Where's your
negative sign.
negative go?
I know, this one time I did it on purpose. I assume that rumble that I heard in the background was a bunch of you telling me I left the negative sign off, right? Could I just tell you, I'm not gonna take time to work it out, but could I just tell you that there are no negatives with the hyperbolics? It works the exact same way as the trig functions, but there are no negatives.
Or just be switching back and forth.
You can switch them back and forth. You can invert them like the hyperbolic sine and the hyperbolic cosecant, but there are no negatives. You know, the way I remember it with trig functions, and I'll bet you remember it the same way, if I'm taking the derivative of any trig function that starts with a c, my answer is negative. Do you remember it that way? If you don't, try it and see if that doesn't help you. And what I'm telling you is, you got to remember here, there are no negatives. There are none. Okay? Now look what we got. Now I've got 1, oops, sorry. I've got cosine, hyperbolic cosine of x squared minus hyperbolic sine of x squared over hyperbolic cosine of x squared. Now, let's just play around a little bit. It looks to me like what I have is 1 plus hyperbolic tangent of x squared. What do you think? What I did is I divided this by this, and what did I get?
1.
Then I divided this by this, and I got 1, and that should be a negative.
And that's our.
Wouldn't it
that's
take
it.
it? Sorry, go ahead.
Either one of you.
Wouldn't it take it like if you when you did the first one, the hyperbolic cosine of x divided by the hyperbolic, wouldn't that just take it out completely? It would just make it 1, and then you'd have minus the hyperbolic sine of x squared. Wouldn't that be your answer?
No, the denominator goes with both of them. That'd be nice, though. Daniel, what were you gonna say?
Oh, I was gonna say 1 minus the tangent squared of x, or hyperbolic tangent squared of x is a trig identity, getting you the secant.
In trig, what is equal to the secant squared?
1 minus tangent squared.
Yeah, 1 plus tangent squared. Ed, you want to give the punchline?
Well, the thing is, I'm trying to remember the identity. The identities are a little more difficult than they are with trig. And I think
Well, here's the way I remember the identities. Do you remember, class? I said first cousin. I didn't say brothers and sisters. don't think so. I'll look.
Okay.
Now Bear's looking. Yes, how'd you know that?
I just remember, it's the thing that confuses me all the time, so.
Evidently it confuses me too. I said first cousins, didn't I? You wouldn't expect them to be the same in every way. Isn't that easy enough to remember though? And that is that sine squared, I'll remember to my last breath sine squared theta plus cosine squared theta is equal to 1, right? You add them together and you get 1 in trigonometry. And then, and for hyperbolics, I remember that you subtract them. And obviously, I have trouble remembering which one's first. Probably won't after today. I think I'll remember for the rest of this semester. If you're adding them, it doesn't matter which one's first, right? But if you're subtracting them, that's being a first cousin, is what subtracting them is. So once I do that, then I don't need and now you can see why this didn't work out for us, right? But I don't need it anyhow, because I know that this is equal to and we're back to being kinfolks again, aren't we?
The first way you did it the right way?
Do what?
First way you did it the correct way to do it?
No, it would be the correct way of doing it, but then I'd have to give you another new identity. And I just as soon limit what I give you. So I took it off in order to use the cosine squared minus sine squared and show you that. What I'm trying to do simply is not give you too much to have to remember, because test 5 in this course